For over a century, paleontologists believed they had uncovered dinosaur mummies, fossilized skin, scales, even hooves, impossibly preserved in Wyoming's barren ravines. But when scientists finally probed beneath the surface, what they found was not actual flesh at all. It was a nearly invisible clay mask sculpted by bacteria as the carcasses rotted, preserving details no fossil had ever shown. Those details revealed the world's first hooved reptile, and they rewrote the rules of extinction. How did a badlands graveyard pull off this evolutionary sleight of hand? The answer begins here, where every clue challenges what we thought we knew about death, decay, and deep time. In the summer of 1908, Charles H. Sternberg, a veteran fossil hunter, trekked into the badlands near Lusk, Wyoming. The ground there was raw and broken, carved by wind and water into deep ravines. Sternberg's team unearthed a skeleton unlike any they had seen, a duck-billed dinosaur later named Edmontosaurus and nectens, its bones wrapped in what looked like dried skin. The specimen, cataloged as AMNH 5060, was shipped east and quickly became a showpiece at the American Museum of Natural History. Archival photographs from those early expeditions show Sternberg and his crew crouched beside the exposed bones, the supposed mummy lying in stark relief against the pale river sand. For decades, this find stood alone, a scientific marvel, the first of its kind. The term dinosaur mummy entered the paleontological lexicon, and the Wyoming Badlands gained a reputation for yielding the impossible. Yet as years passed, the region's promise faded. Field notes and letters from those early days gathered dust, and the exact site slipped from memory. In 2000, University of Chicago paleontologist Paul Sereno set out to retrace Sternberg's steps. Using century-old photographs and handwritten maps, Sereno and his team worked through the labyrinth of ravines, matching landmarks and sediment bands to archival images. Their search paid off. The original dig site was relocated and a broader pattern emerged, a compact stretch of badlands where more than one Edmontosaurus mummy had come to light. This so-called mummy zone became the focus of a new wave of excavation, blending historical detective work with modern science. The groundwork was laid for discoveries that would challenge every assumption about how dinosaur bodies could survive the passage of deep time. The new century brought a different kind of fieldwork to the Wyoming Badlands. Instead of a single prize mummy, teams began uncovering a pattern: multiple Edmontosaurus skeletons, some with their own stories written in stone. Two specimens, both from the so-called mummy zone, became the center of the latest investigation. Their field nicknames, Ed Jr. and Ed Sr., hint at their difference in age and size. Ed Jr., a late juvenile, measured less than a quarter of the adult length, while Ed Sr. was approaching the full 12 meters expected of a mature Edmontosaurus. Both were found in close proximity, their bodies locked in the same ancient floodplain sands that buried the original Sternberg mummy nearly a century before. The details preserved on these two fossils were unlike anything seen since the early days of dinosaur hunting. Ed Jr. showed a surprisingly complete outer contour for such a young animal, while Ed Sr. revealed the full adult profile, including the fleshy ridge and tail spikes that would have made these animals stand out on the late Cretaceous floodplain. The scale of preservation was matched only by the questions it raised. To check whether these finds were truly unique, researchers looked to another famous specimen, Dakota, a hadrosaur uncovered in North Dakota's Hell Creek Formation. Dakota's fossilized remains include large patches of what appears to be real mummified skin, with underlying muscle and tendons preserved by a different set of circumstances. Where Dakota's tissue survived through rapid burial and mineralization, the Wyoming mummies seem to follow a different script entirely. The comparison set the stage for a deeper paradox. Why did so many details survive in the open, oxygen-rich floodplains of Wyoming, where decay should have erased every trace? Scientists have a habit of challenging the impossible. In Wyoming's so-called mummy zone, that skepticism runs deep. When the latest Edmontosaurus fossils surfaced with what looked like intact skin, spikes, and even hooves, the first reaction from experts was blunt. These cannot be real mummies. The conditions just do not add up. True mummification, where skin and flesh dry out and survive for millions of years, requires a rare cocktail of chemistry, climate, and luck. Here, the evidence pointed to something stranger, something that did not fit the textbook. Viewers will notice certain phrases on screen, such as, "Scientists just found a hooved dinosaur in Wyoming's mummy zone," or "Dinosaur mummy exposes how microbes cheated extinction." These are not just headlines. They signal the forensic approach driving this investigation. Every claim, every visual is anchored to evidence. The story is built on what the scans, sediments, and specimens actually reveal, not on wishful thinking, and never on hype. It is important to address a common misconception early. None of the fossils in this documentary are true mummies in the biological sense. What is preserved is not ancient skin or muscle, but something far more unlikely. The term mummy is used here the way it is used in the scientific literature, a convenient shorthand for fossils that preserve the outer shape of a dinosaur, not its original flesh. As the story moves forward, every detail and every claim will be tested. The paradox at the heart of Wyoming's mummy zone is not just about what survived, but about how the evidence rewrites what scientists thought they knew about decay, preservation, and the creative power of microbes. The next step is to examine why, by all normal rules, these so-called mummies should never have existed at all. Decay is relentless in a river floodplain. When a dinosaur dies on open ground, its body becomes a target for every scavenger and microbe in the ecosystem. Carrion birds, crocodiles, and insects strip away flesh within days. Bacteria and fungi break down what remains, turning muscle and skin to liquid. Sunlight and wind dry out exposed tissue, but the real destruction happens below the surface. In a floodplain like the Lance Formation, oxygen-rich water seeps through sand and mud, fueling aerobic bacteria that consume soft parts with ruthless efficiency. What starts as a 12-meter animal can be reduced to scattered bones in a matter of weeks. The Lance Formation near Lusk, Wyoming, is no stagnant backwater. 66 million years ago, it was a braided river system, its channels shifting with every seasonal flood. Every year, the floodplain was refreshed by new sediment and by pulses of oxygen. This is the worst possible scenario for preserving anything soft. In anoxic lagoons, decay slows to a crawl, but here, the abundance of oxygen supercharges the process. Even the largest dinosaur carcasses stood little chance. Once the skin broke, internal organs collapsed, and the body deflated in the heat. Bones could be scattered by water currents or scavengers, and the surface details, scales, ridges, and spikes disappeared almost immediately. Under these conditions, fossilization is a race against time. For soft tissue to survive, burial must be immediate and complete. Yet in the mummy zone, the evidence points the other way. These Edmontosaurus remains were not entombed in mud the moment they died. Instead, they lay exposed on the floodplain, subjected to all the usual agents of destruction. The surrounding sediments are classic river sands and clays, deposited in a system teeming with life and oxygen. There are no signs of stagnant water or chemical conditions that would slow decay. This is the paradox at the heart of the mummy zone. The setting should have erased every trace of skin, crest, and hoof. Instead, the outer contours of these dinosaurs survived, down to the smallest scale. The puzzle is clear. In a place where decay should always win, something intervened. The answer lies in a sequence of events that defies the normal rules of fossilization, a process that begins with drought, ends with burial, and in between lets microbes play a trick on time itself. On the ancient floodplains of Cretaceous Wyoming, the odds were stacked against any body left exposed. Yet, in this stretch of badlands, a rare sequence began to play out, each step locking away details that should have faded. It started with drought. The river retreated, leaving carcasses stranded under a punishing sun. Skin shrank and cracked, the animal's outline tightened as moisture vanished. This first stage, desiccation, froze the outer shape in place, preserving a ghostly silhouette. Then the weather turned. A sudden flash flood tore through the ravine, dumping silt and sand over the dried remains. The carcass disappeared beneath a heavy blanket, cut off from scavengers and sunlight. Decay slowed, but burial alone could not explain what followed. Below the surface, bacteria took over. They swarmed the damp skin, weaving a sticky biofilm across every scale and fold. This was not just rot, it was a sculptor at work. As the microbes multiplied, they released charged molecules, turning the body's surface into a magnet for minerals. In the groundwater, clay particles, each less than 1,000th of a millimeter wide, drifted toward this charged film, pulled in by electrostatic forces. Over days, those particles settled, building up a shell so thin it measured less than a millimeter, yet captured every wrinkle and spike with uncanny precision. As the soft tissue beneath the mask dissolved, the clay template held firm. What began as flesh and bone became a three-dimensional cast, nature's own death mask. Years later, when paleontologists split the rock, they did not find preserved skin but a fragile clay film, so delicate it could crumble at a breath. Paul Sereno described it simply: it is a mask, a template, a clay layer so thin you could blow it away. The twist was what this mask preserved. Every scale, every contour, locked in by a process that relied on drought, flood, and a swarm of microbes working in sequence. The outer body of Edmontosaurus survived not through miracle, but through a natural chain, desiccation, biofilm, and a sub-millimeter clay shell. The final verdict on its makeup would wait for the lab. For now, the secret rested in a shell, barely thicker than paper, holding the last outline of a vanished giant. Lab doors closed on speculation. The forensic process began with the most basic question: what exactly is the so-called skin on these Edmontosaurus mummies? The evidence was put on trial, one method after another. Hospital-grade CT scans revealed a continuous wafer-thin layer, never more than a millimeter thick, wrapped around bone, but always separated by a sharp, clean boundary. Where true mummified tissue clings to bone, this film hovered, as if painted on by an invisible hand. X-ray radiography agreed, showing a distinct density contrast: bone, then a uniform mineral shell, then nothing but sand. Scanning electron microscopy took the investigation to the microscopic level. Under high magnification, the surface broke down into a jigsaw of stacked clay platelets, tightly packed, each no wider than a bacterium. No sign of collagen fibers, no preserved cells, no trace of the biological scaffolding that defines living skin. Thin section microscopy confirmed the verdict: no histological structure, only a dense, featureless mineral layer. Chemical analysis closed the case. X-ray diffraction produced sharp peaks for smectite and illite, the clays of river mud, not the diffuse signature of decayed protein. Elemental analysis by EDS and XRF mapped the surface as a mosaic of silicon, aluminum and oxygen, classic clay chemistry. Carbon and nitrogen, hallmarks of organic matter, barely registered above background. Mass spectrometry and protein assays delivered the final denial. No detectable protein, no keratin, no ghost of original skin. Every test converged on the same answer. The mummy is a mask, not a body. Not a single method found evidence of preserved tissue. The entire outer layer is mineral, a negative mold sculpted by decay and microbes. The lab's checklist grew long: CT, SEM, XRD, EDS, histology, mass spectrometry. Every asset cleared, permissions signed, every image and scan accounted for. The science was unanimous, the paperwork relentless. One paleontologist summed it up with a dry smile. He said, "We've got more permissions than protein." The debate was over. Anatomy would be next in line for cross-examination. The first surprise came from the feet. CT scans of the Edmontosaurus mummies revealed something no one had predicted. Each hind toe was capped by a broad, wedge-shaped structure, flat on the bottom, thickened at the tips, and fused into a continuous surface. These were not claws, they formed a true hoof, the kind of anatomical feature seen in horses and cattle, not in any known reptile. The clay film captured every groove and crease, even the faint outline of a fleshy pad behind the toes. To test whether this was just a fossil oddity, researchers compared the scans to fossil footprints from the same layer of Lance Formation mudstone. The match was uncanny. The footprints were wide and deep, pressed flat at the front with the heavy midline creases and no sign of claw marks. The mummified foot fit the mold, literally matching the shape and proportions of the tracks left in Cretaceous mud 66 million years ago. The study's lead author put it bluntly, "For the first time, we have direct evidence that a giant dinosaur walked on hooves." The technical term is subunguligrade, an animal walking on a hoof base, not on sharp claws or fleshy pads. This is not just a new detail for Edmontosaurus, it is the first confirmed case of a hooved reptile in Earth's history. The evidence is clear, but the implications are just beginning to unfold. Museum walls and textbooks once relied on a patchwork of guesswork to fill in the outer shape of Edmontosaurus. That changed when the clay mask impressions revealed a new silhouette, one that forced a reckoning across the field. The midline crest, once a speculative flourish in artist renderings, is now traced in fossil evidence, a fleshy ridge running from the base of the skull down the neck and tapering along the trunk. Each spike along the tail stands in its original position, the clay film preserving their height and spacing with a precision no sculptor could match. Across the flanks and limbs, scales as small as a millimeter and as large as 4 millimeters form a mosaic, their pattern and size mapped directly from the template. For curators, the implications are immediate. At the University of Chicago Fossil Lab, the lead preparator began drafting new guidelines for life reconstructions. Museum mounts, once built on bone and inference, now require digital overlays of the clay-contoured crest and tail. Artists are redrawing the animal's profile, correcting the trunk's bulk, the tail's cross-section, and the exact placement of that midline ridge. The clay mask has become the blueprint, no longer a curiosity, but the standard for how Edmontosaurus should appear in every exhibit and illustration. Behind the scenes, curators are already planning rescans of older specimens, searching for overlooked traces that could further refine the public face of the dinosaur. The process is ongoing, but the days of guesswork are ending, one clay impression at a time. Today, the fossil record is still being rewritten, not by new bones, but by deciphering the mask's microbes left behind. As advanced imaging exposes what is real and what is illusion, every so-called mummy may hold another evolutionary twist we never expected. In a world shaped by decay, even extinction leaves its fingerprints. How many more secrets are hidden in plain sight, waiting for someone to look twice?